Hello, everyone. It is 8 p.m. GMT, and I would like to welcome you all to VSAONLINE webinar series. Today, it is my great pleasure to welcome Rasmus Pagh, Professor Pagh from University of Copenhagen in Denmark, who will be talking about sketching of polynomial kernels. So I look forward for this exciting talk. So Rasmus, please, the floor is yours.
So thank you very much for the invitation and this opportunity to speak about kind of a topic that I was very excited about some years back. It's still something that I really enjoy talking about. So it was nice to have this opportunity, even though some of these results are, from back in 2013, have an opportunity to share some of these things with you. So what I'm going to talk about is joint work with my former student, Nin Pham, and also joint work with Ale, Kapradov, Horn, Vellinker, Woodruff, and Sandier. Basically a merge of the two papers that ended up with a lot of papers and appeared in SODA Symposium on Discrete Algorithms in 2020. So before we start, I wanted to say a little bit about myself, just to make sure that you understand where I'm coming from. So basically, I did my PhD in theoretical computer science, in particular in design and analysis of algorithms. And I kind of started specializing in randomized algorithms. I did my PhD on design and analysis of hashing-based dictionaries. I worked on sketching and more lately differential privacy. In the world of kind of high-dimensional data, I had an ERC project some years ago on high-dimensional similarity search. So I thought a lot about kind of high-dimensional phenomena. I was also a visiting faculty researcher at Google Research in California some years ago, lived in Berkeley. So I might have met some of you over there. Unfortunately, I don't know a lot, well, not a lot at all about vector symbolic architectures or high-dimensional computing, but I'd love to learn more about it. From what I can tell, at least, there seems to be a lot of themes shared with TCS work on sketching and probably also other aspects. So let's get started. So we'll start with something simple, and probably this is going to look familiar to things you have seen, but just to kind of establish some ways of thinking about things that we'll be using throughout the talk. And the appetizer is about counting things. Okay, so let's consider a toy problem. So we have a collection of objects, and we want to determine how many there is of each kind. So basically, we want to have a representation of a histogram. So saying, for example, that there are 3 cars and 2 teddy bears. And, this is easy stuff. You learn in the first semester in computer science or computer engineering programs how to do this. You can sort, you can maybe build a hash table to keep track of these counters, and this is kind of easy peasy. But now let's make it more challenging, because in some situations we are actually not able to just access the collection of objects in any way we want. Let's consider the situation where you're only allowed to look at each object once and only one at a time. Okay, so basically this models situations where maybe you don't have the storage to store all these objects, or for some reason you need to compress the information down. Okay. So we kind of basically pass over all of these things. And furthermore, we only want to remember one integer. Okay. And just to avoid kind of tricks, encoding a lot of information in a single integer. Let's say that this integer is of no size n, where n is the size of the collection. Okay, so we could store something like 42 if 42 is less than the number of objects, right? So if we know that we are looking for the number of airplanes, of course, we can kind of easily do that with the counter. Each time we see an airplane, we increment the counter and so on. And once we have passed through all the objects, we know that there are four airplanes. But now let's consider a more general problem, because in general, we may want to do some kind of weighted counting. So the case where we are just looking for airplanes would correspond to assigning a weight of 1 to airplanes and 0 to everything else. But in general, we might be interested in multiple things, or even more generally, counting with weights. And now we're going to do something that seems a little bit weird if you haven't seen similar ideas before. So we are going to assign random weights to objects. Okay, so basically, every time we see a horse, we're going to count it as -1 occurrences. Every time we see a teddy bear, we're going to count as 1 occurrence. And now we can kind of, assuming that we have access to these weights, we can maintain a counter. We see a horse, we subtract 1. We see an airplane, we subtract 1. We see a teddy bear, we add 1, and so on and so forth. So for each object, we add its weight, and we end up with some number, in this case, 0. Okay. And now, yeah. So the question is, why would you want to do something like this? Because kind of on average, we end up with nothing, right? So we ended up with 0 in this example, and this is exactly what we expect. So since these counts are random, each object contributes 0 to the counter. The expected value of what we get out is 0, right? But now there's something like a magic trick, and I know that this is similar to some of the magic in VSAs, which is that if we multiply by one of these counters, we actually get something that has a positive expectation. So multiplying the counter by the sign of the airplane gives you a value that in expectation is exactly the count of the airplane. Okay, and this is easy to kind of verify, and this is simply because, whether the counter is -1 or +1, if you multiply it with itself, you get 1, and kind of the expectations for everything else is unaffected, assuming that these things are independent. Okay, so that's very nice. So it seems that we can in fact get something out of this, but isn't this too good to be true, right? Did we just get some kind of infinite compression? Because we can of course do this with all the objects. We just have one counter, but we can get something that has an expectation that is the number of cars. We can get another expression, which is the number of airplanes in expectation, and so on and so forth. And this was analyzed in the 90s, exactly this, by Alan Gibbons, Matthias, and Szegedi. And of course, the reason, or the but here, the caveat, is that the variance could be, and in fact will be high. And one of the results in these papers is actually that it's inevitable. No matter what you do, if you compress information into a single counter, then somehow the variance needs to be this high, and there's no way to get smaller variance than what you get from this particular way of sketching these counters. But somehow we can hope to maybe tame the variance, do something to reduce it, maybe storing some more information. And there are basically 2 ways of doing this. So the first one is, it's a very general thing. If you have something random and you want to it to be more reliable, you can basically do independent repetition. So in this example, we would take random independent weight functions, S1, S2, up to Sk. And for each weight function, we get an independent weighted sum. And now we can kind of combine. We get a lot of estimators and we can combine them. And there are at least two ways of doing it. Well, there are more, but kind of the two most obvious ways of combining these estimators is by averaging or by taking the median. So averaging has the advantage that it reduces the variance, but you know it's also something that's relatively expensive. So if the variance is large, we have to average a lot of things to get the variance low. So taking the median has kind of different properties. It doesn't necessarily reduce the variance, but it increases the reliability. So the probability that your estimate is much worse than what would be predicted by the variance becomes quite small if you take a median of several estimates. So the second idea, so this is kind of maybe the most obvious idea, if you like. Second idea, which is I think slightly less obvious, is that it can actually help to split into subproblems. Okay, and here the idea is that we use some random function again, and this time it's a function that tells us for each item which subproblem does it belong to. So in particular, we have a random function, a hash function h, that maps each item to one of b values. And basically, depending on what value you hash to, you kind of affect, you end up with one of these parts, which are then handled separately, for example, using a single counter. So in this case, for example, the robot ends up in a separate part, and we actually get an exact estimate for the number of robots based on that part. But of course, in general, there's still going to be collisions. We may have, multiple counters with signs in each part. So what do you get? What do we get if we combine these techniques? So this was studied kind of in the early 2000s by two groups of people. So first in the TCS community by Charikar Chen and Farrokh Coulter in 2002. And then later on, independently in the machine learning community, Weinberger, Dasgupta, Langford, Smola, and Attenberg presented exactly the same construction. And I'm going to give a kind of a self-contained description here, but basically what is going on is exactly what I said before, that we are combining these techniques that we saw. Okay. So what we want is to somehow map all these counters. So this histogram is a d-dimensional object, so that d different counters we want to represent, and we want to somehow map this to a lower dimensional vector. And we are going to think about this lower dimensional vector actually as kind of a two-dimensional array or matrix, if you like. So with k rows and b columns. And the idea is that kind of the entry number L of the vector affects one entry, one and only one entry in each row of this sketch. And we use a random sign for each row. And these, the position and the sign are, again, determined by hash functions. So in the first row, we use one hash function h1 to decide where do we store hl or information about hl, and we use another hash function s1 of l to decide whether we store with a sign of +1 or -1, and similarly for every row. So we basically have k hash functions for determining positions, and k hash functions for determining signs for each possible item out of these d items. So in kind of more compact notation, if we look at entry number I, j, so row I, entry column j, what we have there is a sum of items whose hash value under the hash function hi is equal to j, multiplied by a sign value si of l, and that's and all of this is weighted by xl, so the lth entry of the input vector. So you can see that this is something that's linear. So if we kind of have two vectors and add their sketches, we are going to get the sketch of the sum of the vectors. If we multiply a sketch by a scalar, we get a sketch of the scaled vector. Yeah. So as I said, this is in these papers, they were both quite influential. So Charikar et al. Called it count sketch, and Weinberger et al. Called it feature hashing. So I'm just going to use the name feature hashing for the rest of this talk, but it's really the same thing. They, funnily enough, they don't use the same way of estimating from the sketch. So in the Weinberger et al. Paper, so in feature hashing paper, they use averages. This is because they are more interested in things like dot products. And in the Charikar et al. Paper, they use the median estimator because they are more interested in kind of high probability guarantees. Okay. So what are properties of this count sketch or feature hashing? Well, I just mentioned linearity, but also it's easy to see that in expectation, dot products are preserved. So if you sketch two vectors and compute the dot product of the sketches, you get an unbiased estimator for the dot product of the original vectors. And this is important in some of the machine learning applications. Another nice property is that if your input vector is sparse, then actually the count sketch is also reasonably sparse, of course, depending on this parameter k. If you have a t-sparse vector, it becomes tk sparse. And I think in a lot of cases, we can think about k as being rather small. I mean, maybe even a small constant like 3 or 5, but at most 30 or so. There's also been a lot of work on showing that count sketch can be used as an oblivious subspace embedding. So it kind of preserves dot products not just with high probability, but actually for whole subspaces with high probability. Of course, assuming that these parameters are high enough. So there are some limits to how much you can compress this. So this was a little bit of background on sketching methods. And this was, as I said, this is all kind of early 2000s. So now let's move on to the main course, which is TensorSketch. And to motivate TensorSketch, I'll start by talking about kind of a way of somehow encoding more information or making information more explicit in a vector representation. And let's suppose that we have n features, so it could be counts of different items. And there is a technique used in some machine learning algorithms called bilinear pooling. It may have other names as well, but the basic idea is very simple. So we basically want to combine all pairs of features into new features. So this is an outer product operation, basically. So if we start with n features, we end up with n squared features corresponding to every pair of features, and kind of the weight of a feature is the product of the corresponding features. So this kind of gives an explicit representation of whether, you know, two features are present, for example. Now there's one feature that is kind of activated if two features are present, and this makes certain learning tasks easier. Now, of course, n squared dimensions may be too much, so it's kind of tempting to somehow decrease the dimensionality. And as you probably know, exists a lot of dimensionality reduction techniques. Ken Clarkson talked about this some months ago in this seminar. But actually, you can think about feature hashing or count sketch as one dimensionality reduction technique. So let's use that one and map this whole n squared dimensional vector down to m features. So now we have these nice properties still that, you know, we can estimate the number of or the weight of a pair of features. We can compute dot products between vectors of this form, and so on. But of course, this seems kind of expensive, right? So we create this big n squared dimensional vector just to end up afterwards with a much lower dimensional vector. So the idea behind TensorSketch is basically to make a shortcut. Okay, so we want to go directly from the input vector to the feature hash of this intermediate vector. And it turns out that there's a surprisingly simple algorithm that actually does this. Okay, and it's simple enough that it fits in one slide. So, and the idea, I should say, actually appeared a year before in a paper at IGCS 2012, but then Neil and I realized that actually it was applicable in more cases. So yeah, so the idea is the following. So we take hash functions, one for kind of yeah, so we take hash functions S1 and S2, sign functions and H1 and H2, and then we basically compute a count sketch twice. So once with S1 and H1, and once with S2 and H2. Okay. And the way this is presented in this IGCS paper is kind of slightly more general. Here we think about it as a matrix product, which in turn can be thought of as a sum of outer products. And now the idea is the following. So I hope you can see my cursor. So we can think about a count sketch as a polynomial. Okay, so here we have for each entry in a vector here, AI, we have its sign S1I, and this sign belongs to is a coefficient of x to the h1 of I. So this is another way of saying that this value is stored in position number h1 of I of an array. So you can kind of map back and forth between coefficients of a polynomial and kind of a count sketch stored as an array. And then we simply sum this over all the entries. And now if you want to think about matrix products, there's an extra sum, but for now, just ignore this outer sum. So basically, then we have a count sketch of one vector here, encoded as a polynomial, and we have another count sketch here, encoded as a polynomial. And now we simply compute the product of these two polynomials. And in the particular case of bilinear pooling, these two vectors, A and B, are actually going to be the same vector. So it's the same vector that is being sketched twice with different hash functions. And we compute the product and extract the coefficients. And let's say that Ci is the coefficient of xi, x to the power I, in the product. Now I claim that there's a simple way to extract an unbiased estimator for entry number ij in the product of A and B. And so to do that, I claim we locate a particular entry in this polynomial, namely the coefficients of x to the power h1i plus h2j. And we multiply that by the product of the sign functions s1 of I times s2 of j. So let's try to see why this is actually unbiased. Yeah, I forgot to mention that you can kind of see that each coefficient here is a sum of entries of A and B with random signs. And this is basically because we have an outer product here. So basically every combination of some entry of A and some entry of B, because they share the same value k, is going to be part of the matrix product AB. Okay. So to see that this is unbiased, all we need to observe is that if we multiply these sign functions, so a product of S1 of I1, S1 of I2, S2 of J1, and S2 of J2, the only way we get something that's 1 in expectation is if the I1 is equal to I2 and J1 is equal to J2. Otherwise, one of these things is going to have expectation 0 and be independent of the other things. So basically, when we compute this estimator, there's going to be a lot of things that have like a 0 expectation. So by definition, what we're looking for is the expectation of this expression. But basically everything is going to have expectation 0 except those terms where kind of S1 of I matches S1 of I in here, and S2 of J matches S2 of J in there. So we basically get only those terms. And furthermore, we get like S1i squared and S2j squared, which again is just 1 as before. So what we get is indeed the ijth entry, and the power of x in the polynomial is exactly x to h1 of I plus h2 of j. So of course, unbiasedness is not enough to make this useful. We also want to know something about the variance, and it turns out that it's not too much more complicated to analyze the variance. So basically, what we want to analyze is, how much noise do we expect in the estimator. So we can look at some entry at position I prime j prime in this matrix product, and kind of the only way that we get something with, I think this should say expected value. So the only way that we get something with expected value that is non-zero is, again, if we have a collision, but this time it should be a hash collision. So, if the sum of hash values of I and j is equal to the sum of hash values of I prime and j prime, then I prime j prime contributes to the noise. But basically, again, this is a random event that happens with probability 1 over b. And furthermore, these are kind of uncorrelated, so we can compute the variance just by summing the variances of events. So basically, what we get is that we get a contribution to the variance of the I prime j prime value squared divided by b. So divided by b is because there's only like a probability 1 over b that we get this contribution, and squared is because the variance is just the expectation of the noise squared. And another way of writing this is that the variance is the Frobenius norm of the matrix product divided by b. So if we can bound the Frobenius norm and choose b suitably large, we can control the variance. So that was kind of how we can get bilinear pooling to work kind of directly. So we just sketch twice independently and compute a product of two polynomials. And now, of course, if you do the polynomial multiplication naively, you end up with something that is as expensive as doing bilinear pooling. So you need to know some tricks. And the trick that you have probably seen before is to use fast Fourier transform. Okay, so instead of multiplying these polynomials kind of directly, we apply convolution using fast Fourier transform, and this uses time b log b because we have polynomials of degree b. Okay. And in case we want to use this n times, so sketch n outer products to be able to sketch a whole matrix product, we end up with a time of n squared plus nb log b. And I have a few slides kind of from back in the day, so you can apply this to find correlation, for example. So here is a matrix, and there are two rows that are correlated. It might be hard for you to see which ones. Of course, one can compute the sample covariance matrix, and here we actually see that there is something that sticks out, a pair of entries that have a high dot product. And it turns out that even if you estimate this using compressed matrix multiplication and kind of sketch this whole matrix rather than compute it explicitly, you actually get a signal that is strong enough to actually give you a reasonably small list of candidate pairs that you can then check for correlations. So this is not like a state-of-the-art algorithm for this problem, which is called the light bulb problem, but it's a simple one. All right. So this was kind of sketching an outer product, or bilinear pooling, if you like, and one can easily kind of generalize this to arbitrary polynomials. So in general, the goal here is we have some polynomial like x cubed plus x or something like this, and the goal is to create a sketch. Let's call it TS for tensor sketch, such that if we compute the dot product of two sketches, the value is approximately this polynomial applied to the dot product of the input vectors to the sketches. And it's kind of easy to see in principle that this is possible, because there are kind of embeddings that give you exactly this property if you go to high enough dimensions. So basically there exist embeddings that increases the number of dimensions from n to the power p with the property that you get dot products. If you multiply two of these embeddings, you get a dot product that is exactly this polynomial applied to the dot product of the original vectors. And as before, we can use feature hashing or any other dimension reduction techniques in order to kind of scale this down into a more manageable size. And just like before, TensorSketch kind of works. So now we need to do the convolution not of 2 count sketches, but of p count sketches. So basically using Horner's rule, but it's basically exactly the same thing that is going on. So instead of having to create these n to the p features directly, we kind of do something in, we can directly compute this kernel approximation in near linear time. Okay, so this turns out actually to be useful enough that it's been implemented in scikit-learn. And one of the reasons that they are interested in this is kernel trick that you probably know about. So there are cases where, for example, in classification problems, it's hard to find a good linear separator. So for example, here's a classification problem on the left where we want to classify whether a point is red or purple. And there's no linear classifier. There's another shape, circle, that classifies the points well, but we don't have a linear classifier. But it turns out that you can kind of embed these vectors into a higher dimensional space, in this case 3-dimensional, such that suddenly there's a linear classifier that actually works. So for some classification problem, it helps a lot to kind of look at some polynomial kernel that somehow makes the problem richer and easier to solve using techniques such as support vector machines. And here's an example for particular classification problem, not a particularly difficult one, I think, called cover type. So if you try to solve it directly on the raw data, you get a certain accuracy. And if you use a kernel, you can kind of boost the accuracy significantly. But unfortunately, kind of this kernel SVM, if you implement it naively, it's not efficient. So it basically requires at least quadratic time. So now the idea would be instead to use these kernel approximations. And here they have been tried with various sizes. So this is the number of dimensions in this vector that represents the approximation. And you can kind of see that the more dimensions you add, the closer you get to the accuracy of the kernel SVM. Right. Okay. So I think I'm almost done. So I wanted to mention this a bit quicker than I thought, but let me just end by mentioning a few further developments. I'm not going to say too much about them, but a little bit. So one kind of disadvantage of what I've talked about so far is that there's a kind of a bad dependence on the degree of the polynomial, in the sense that if you use this for a high degree polynomial kernel, you get quite a high variance. So the variance grows exponentially in the degree of the polynomial. So if you want to use this for polynomials of more than degree 2 or 3 or maybe 4, then the variance becomes pretty high. But it turns out that this is not inherent. I mean, so you can basically fix this. And the key idea here is to use some kind of recursive technique, basically. So instead of basically using Horner's rule and kind of increasing the degree one at a time, you can basically use some kind of divide and conquer. You have to be a little bit careful that the dimension doesn't blow up too much. So basically put some dimension reduction in between, but more or less this works, and this then gives a variance bound that is polynomial in P. Another thing that has been studied is, the running time, whether it can be made independent of P, and for most parameters, it actually can. So this was in ICML21. So basically, P is now part of the variance, but not of the running time. So it is possible to sketch polynomial kernels of very high degree efficiently. And well, that's all I had. Thanks for listening. And if there are any questions, I'm happy to hear them.
Rasmus, thank you very much for this talk. Thank you very much indeed. So now I open the floor for questions. Are there any questions?
I have a question. I was wondering early on in your presentation, thank you, by the way, for a very nice presentation. You were talking about the Weinberger method using the average of multiple count sketches or the rows of the count sketch versus the what is Sharikar method that used the median. And I was wondering, why would there be an advantage to using averages of rows compared to just adding more bins?
Okay, so right, so that's a great question. So if I understand the question correctly, so you instead of having k rows here and kind of averaging them, why not just have k times b bins? So basically have a single row. And
exactly,
I think yes, and I think the answer is that I think the variance might actually be exactly the same. I mean, it's decreased by a factor of k in both cases. I mean, increasing the number of bins by a factor k is the same as kind of repeating k times and averaging. So I think the advantage is maybe more in the tails. So if you care about the probability of really bad things happening, then I think you get, I mean, if you only have one repetition and you have a hash collision with some kind of large entry, then you get a really big error. Whereas if you kind of repeat k times, you may get one big error, but you probably don't get k big errors.
But for this scenario, the median would work even better, no?
Yes, that's right. So in terms of kind of controlling the tails, the median is definitely better. But the thing about the median is that it's not a linear operation. So actually, the median operator doesn't really work with, for example, the SVM application. So there you because there you somehow need to you need this property that dot products actually are what approximates your kernel function.
I see.
So it's actually an interesting question. Are there better ways of making these things reliable, right? Because somehow, yeah, the median is is nice, but it's a very non-linear technique. It's also not, something you can easily put into neural network model. As far as I know, people don't boost probabilities in neural networks by taking the median of many estimates. And I guess that's a reason for that. That it's difficult with these non-linear functions.
Just one quick follow-up to that. What about using the min, like in min sketch?
Yes. Okay. That's also a very good question. So we have, there is this variant of count sketch called count min sketch, where basically we don't have the sign functions. And in the case where we have non-negative entries, vectors with non-negative entries, we can get an effect similar to the median by taking the minimum of several estimates in order to boost the performance. So actually, this tensor sketch idea also worked with count min sketch in principle. So you can you can compute the convolution of count min sketches and get a count min sketch of say an outer product, for example. But it seems, I never really got around to looking at this in detail, but it still seems like kind of count min sketch is less noise robust because its noise scales with the L1 norm of the input vectors, whereas count sketch scales with the L2 norm of the input vector, so the noise. So so I'm not sure if you can get something like practical out of it, but in principle you could definitely do similar things with count min sketch.
Thank you. Thank you.
Thanks for your talk, Rasmus. I have a question that is probably maybe a bit naive, but because in vector symbolic architectures we often do something that is very similar to sketches, like summing together, trying to make kind of a coarse representations of several objects. And I guess when it comes to polynomial kernels, one might like to kind of assign weights to different polynomials. And of course, it's trivial to assign weights when we have the feature map explicitly. But I was curious if there are any attempts to try to do it once we already created the sketch. Do we have any hope to now modify something within the sketch, or are there any tricks that one can use to try to do it?
Okay. Well, I'm not. There are certain things you can do with sketches because they are linear, right? So you can definitely you can multiply the sketch by a constant, for example, and that would, I suppose, correspond to changing the weight. But I suspect that you are after something more powerful than that.
Right, because that multiplying by scalar would change the weight of all the monomials that we have in this case, right? And let's say we want to change only a couple of them.
Oh, I see. Right, I see. Yes. So you imagine like a polynomial with kind of potentially many terms.
With potentially, yeah.
Yes. That's a good question. I'm not aware of work in that direction. I mean, of course, one thing you might do is to have multiple sketches of different polynomials, which you then kind of combine into a sketch of a particular polynomial. So that's possibly one technique, but I'm not sure how far that gets you. So it's a good question.
Thanks.
Dmitry, please.
Yes, such a question. And are there any possibilities to make the sketch binary? Maybe the price of increasing dimensionality, of course.
Yes, I like that question too. I think it's possible, but I mean the closest techniques, which I'm sure you are well aware of, is SimHash, which is a technique for binarizing, you know, a single vector. And I suppose that it might be possible to somehow combine this with SimHash, but I have to admit that I haven't really thought about it. But at least in principle, you know, you could take, you know, the whole sketch and compute the SimHash of the sketch, and that would give you some binary representation, or compute a number of SimHashes of the sketch, and that would give a binary representation where there is like a one-to-one correspondence between the dot products of the sketches and the kind of the dot products of the binary vectors. At least assuming that we have normalized the vectors.
Well, thank you. Very interesting.
All right, let's see if we have more questions in the audience.
Yeah, is there an element of compression in what you're doing here? And if there is, I was wondering how it compares to, you know, simple techniques like PCA.
Okay, that's also a good question. I mean, I always like to think about these as compression, lossy compression. I'm afraid I don't know much about theoretical results around PCA, so I don't know if I'm able to make a comparison. But I mean, maybe one observation here is that you know, what I talked about basically doesn't exploit any properties of the data. So there's no, you know, yeah, if there's any structure, it's basically destroyed completely by the sketch, because there's so much randomness, whereas PCA and other techniques work because there is structure in data. So I think it would be pretty interesting to see if some of these techniques could be improved in kind of a data-aware sense, that maybe it's possible to yeah, simply do things better if there's structure.
Right, yeah, because you don't try to tune the parameters to like reduce the variance, do you?
No.
Yeah. Okay.
I think maybe the closest thing to what you are asking about might be these results about oblivious subspace embeddings, showing that some of these sketches actually, if you are sketching, you know, vectors from from a low dimensional subspace, for example, then you do get, you know, guarantees over the whole subspace, even though it has infinite size, and you are using you know, an algorithm that has an error probability, then basically there's a high probability that actually works for the whole space.
Okay, thanks.
I had another question about the independence of the hash functions. In what you showed just now, it looked like you used pairwise independence for the signs and three-wise independence for the bin hash functions. But I've also seen in
That's right.
papers people use four-wise independence for the signs and then two-wise independence for the bins. Would you comment on why these different approaches are used? And
right. I think if you want to be on the safe side, then probably you want four-wise independence. I have to admit it's been a while, so I'm not sure if I should try to comment on that. But there are some subtleties, and actually even a mistake. I mean, in the 2013 paper, the analysis is not correct exactly because of an independence issue, but it's fortunately it's easily fixed, so fixable.
right, because if you could go away with two-wise independence for the signs and then three-wise for the bins, this would implementation-wise be better than four plus two-wise, right?
Yes, that's true. I mean, however, there are pretty simple classes of hash functions that are four-wise independent. So, for example, there's a technique by Torp and Chang, I think, that is based on table lookups, which is super fast. So I don't think, I mean, I don't think it should be a bottleneck in practice to evaluate the hash functions.
Okay, thank you.
But is it really necessary in practice for theoretic estimations, of course, but in practice, am I understand correct that I could use just any random number generator and it works?
Yes, I mean, unless your data is adversarial, I would say, then most likely you're going to be fine with any reasonably good hash function.
Thank you.
All right. So let's see, maybe we have a room for one last question because it's getting late here in Europe. Well, if not, probably it's a good time to wrap it up. And I thank you, Rasmus, once again for being with us and giving this excellent talk. So, and thank you all for attending. So
It was a pleasure. Yeah, thanks so much for inviting me.
All right, I hope maybe inviting you once more time sometime in the future. Let's see. But thank you all for attending. So I see you in 2 weeks from now. So stay tuned.
Yeah.
And goodbye.
Thank you.
Bye.